Hey guys, welcome back. Today we are going to be doing final exam review with focus on integration, being indefinite integration and definite integration. So all we're going to do this video is I have about 12, 13 examples that I want to go over with you, and we're just going to go through them step by step and seeing all the different techniques we use when we are integrating functions. All right? Seem straightforward? All right, let's get straight to it. So, same way in all the videos I've been doing for this final exam review, I will pause the video and then write out the question, and then we will work it out and see how we go about solving these kinds of problems. All right, first function up to bat, we have the integral from 1 to 4 of 1 divided by 2 times the square root of x. All right, so this one, no fancy tricks, no special formulas. All we're going to do is rewrite the square root of x in terms of its power, or the exponent, and then just use the power rule of integration. So let's try this. So this is equal to the integral of 1 to 4 of 1/2 times x to the negative 1/2. Get the 1/2 from the square root and the negative from the fact that it's the reciprocal. It's in the denominator, and then we're integrating with respect to x. Remember that dx is not just a placeholder. It's not just decoration. It serves a purpose. It is an actual operator that is working with this integral symbol. They are working together to do this problem. So we have this now. And now you do not have to do this step. I just do it because I'm me. I like to pull my constants out in front so I don't have to worry about them. And just leave them out there and I'll deal with them in a minute. So this is 1/2 the integral from 1 to 4 of x to the negative 1/2 dx. Now, here, all I have is the integral of x to the negative 1/2. First step now is to find the antiderivative, and then we will deal with the endpoints. So right now, we're just finding our antiderivative. So this is equal to x to the negative 1/2 over plus 1 over negative 1/2 plus 1 multiplied by that constant we have 1/2, and then we have to use our funny notation for the fundamental theorem of calculus, where we evaluate this indefinite integral at 4 and 1, subtract them, and then that is our value. Now this is equal to x to the 1/2 over 1/2 times 1/2 from 1 to 4. Now here we have a 1/2 multiplying a 1 over 1/2, so those terms are going to cancel. So this is equal to the square root of x from 1 to 4. Now all we did was find the antiderivative square root x. Now we have to do the fundamental theorem step, where we take these two endpoints, plug them into our antiderivative, and take their difference. And that'll give us our definite integral. So this is equal to the square root of 4 minus the square root of 1, which is equal to 2 minus 1, which is just equal to 1. So that's all there is to it. Pull the constant out front, rewrite the 1 over square root of x as x to the negative 1/2. Apply the power rule of integration, and then simplify, and then evaluate the antiderivative at the two endpoints, take their difference, and that gives us our definite integral. Now, in relationship between the definite integral and this value, what is this value to the definite integral? Well, 1 is equal to the area under the curve, where the curve is given by 1 over 2 root x on the interval 1 to 4. Remember, the definite integral is calculating the area under a given curve on a specific interval, i.e. the limits of integration dictate your interval, and this function is the curve, and we're measuring the area under it. And so in this situation, that area is equal to 1. All right, that's it for that problem. All right, now let's look at our next example. The integral from 0 to 1 of 3x squared with respect to x. All right, so let's get straight to it. Once again, because I'm me, I like to pull my constants out in front. So I'm just going to go ahead and pull that 3 out in front of this integral. So this is 3, the integral from 0 to 1 of x squared dx. Now it's just a constant times the integral of x raised to some power. So we want to use the power rule of integration. So this is equal to 3 times x to the 2 plus 1 over 2 plus 1 evaluated from 0 to 1. Remember, the power rule, add 1 to the exponent and divide it by the new exponent. So we add 1 to the exponent to get 2 plus 1, then we divide by that new exponent, 2 plus 1, to get our antiderivative. So this is equal to 3 times x cubed over 3 evaluated from 0 to 1, but notice we got 2 3's, so that's equal to x cubed evaluated from 0 to 1. So in this situation, x cubed is our antiderivative of 3x squared. A good way to check that, take the derivative of this antiderivative and make sure you end up where you started. It's always a good trick to do when you're doing these integral problems. When you have your antiderivative here, take the derivative. Make sure you ended up where you started, because if you don't, well, then something went wrong. All right, so now we have our antiderivative and our 2 endpoints. So now we're going to plug them in and take the difference. So this is equal to 1 cubed minus 0 cubed. Well, that's just equal to 1 again. Man, I'm really original here. So what this problem is saying is the area under the curve 3x squared on the interval 0 to 1 is equal to 1. And that's how we go about solving a problem like this. All right, example number 3. The integral from 1 to e of x squared plus 1 divided by x. So we're taking the integral from 1 to Euler's number e. Remember that it's that transcendental number, that irrational number. It's like pi, but better. Of the function x squared plus 1 divided by x. All right. So I don't know about you. When you see a situation like this, I know when I see it, all I want to do is cancel it. See, I got that x squared plus 1 divided by x. What I want to do is break this fraction up. So I get the integral from 1 to e of x squared over x plus 1 over x dx. Why did I do that? Because now I can cancel one of those x's. So this becomes the integral from 1 to e of x plus 1 over x dx. Now that looks something much easier to handle than that first situation. Now from here, I'm going to use the linearity of the integral, and I'm going to pass the integral to both terms. Remember, it's just like differentiation. The integral of the sum is the sum of the integrals. So this becomes 1e x dx plus the integral of 1e 1 over x dx. Now I like to point out that step's not necessary. You can go ahead and do the evaluation of the integral right here. You do not need to break it up like this. I'm doing this to illustrate a point. So if I find it's always safer to do all your steps, but if you get comfortable with this and you feel like you don't have to do this separation right here, go for it. Now, this is equal to the integral from 1 to e of x. Well, x is just x raised to the power 1. So we have to use the power rule of integration again. So we get x to the 1 plus 1 divided by 1 plus 1 evaluated from 1 to e plus. Now, we could do the power rule here, but that power is x to the negative 1. So that means in the denominator, if we did the power rule, we'd have a negative 1 plus 1, which is a 0, which is division by 0. And that's a real big problem. I've been listening to this entire semester. I usually complain about division by 0 once every other lecture, assuming it's that infrequent. So we have to use a different rule here. Well, thankfully, we already have a rule for the integral of 1 over x. That's actually equal to the natural log of the absolute value of x evaluated from 1 to e. Remember, the derivative with respect to x of the natural log of x is equal to 1 over x. So to undo it, we take the integral, we're going from 1x and back to the natural log of x. But why the absolute values? Well, that's because 1 over x doesn't mind negative numbers. You can plug in negative 2 into 1 over x. That's just negative 1/2. But the problem is the natural log only exists for positive real numbers. You can only plug in positive numbers into the natural log. Otherwise, you'll break it. So we have to add these absolute values here as a safeguard to prevent that from happening. All right? So it's one of those details that is actually really important, but equally easy to miss. So now from here, just to simplify, we get x squared over 2 from 1 to e plus the natural log of the absolute value of x from 1 to e. Now we do the fundamental theorem step where we actually evaluate the endpoints. So this first one is going to become e squared over 2 minus 1/2 plus the natural log of the absolute value of e minus the natural log of the absolute value of 1. Right? So this is going to be equal to 1/2 times e squared minus 1 plus the natural log of the absolute value of e, but the natural log of e is just 1. And then we have minus the natural log of the absolute value of 1. The natural log of the absolute value of 1 is just equal to 0. So this is minus 0, and I regret combining that function right there. So let's just leave this as e squared over 2 minus 1/2. And then we get plus 1 minus 0. Well, that's just equal to e squared divided by 2 plus 1/2, because that negative 1/2 and that plus 1 become positive 1/2. And then we can go ahead and pull out a 1/2, and this becomes 1/2 e squared plus 1. And that is our definite integral. See this fraction? We divide up this fraction, cancel like terms, pass the integral through, integrate term by term. This first situation is just the power rule of integration. This second term is 1 over x. We do not have the power rule for integration for the exponent -1, so we have to use a different rule, which in this case is the logarithm rule. And so the integral of 1 over x is just the natural log of the absolute value of x. Then we do the fundamental step where we plug in the two endpoints, take their difference, combine them, simplify, and we get our result, 1/2 e squared plus 1. So that's it for that problem. Alrighty, now let's try this problem. The integral from 0 to pi of cosine of x plus sine of x dx. Alright, so what we want to do here again is the linearity rule again. The integral of the sum is just the sum of the integrals. So this is, good lord, the integral from 0 to pi of cosine of x dx plus the integral from 0 to pi of sine of x dx. Now this is just equal to, now to integrate 0 to pi of cosine of x, you got to be careful here. The derivative of cosine is negative sine, but the integral of cosine is just sine of x from 0 to pi. Got to be careful here. Remember the operation you're doing. The integral of cosine goes to sine, and the derivative of cosine goes to negative sine. So you got to be careful if you're taking the derivative or the integral. Got to make sure you don't make that mistake. Plus, now, the integral of sine of x, you're going to want to say is cosine of x, but it's not. The integral of sine of x is actually negative cosine of x. How can you check these? When you integrate it, you get your antiderivative. Take the derivative of your antiderivative. Make sure you end up where you started. The derivative of sine is cosine. The derivative of cosine is negative sine. So negative sine is just sine of x. So that is our antiderivatives. So when we do the antiderivative step, we get this integral is equal to sine of x from 0 to pi plus negative cosine of x from 0 to pi. Now, plug in the endpoints. We get sine of pi minus sine of 0. And then I'm going to go ahead and pull that minus out in front. Minus cosine of pi minus cosine of 0. Well, this is going to be equal to, now what is sine of pi again? Well, this is where knowing your unit circle is going to come in handy. You got to know that unit circle. If not for my class, you got to know it for Cal 2, Cal 3, advanced mathematics for engineers, differential equations. Any math you take from here on out, you're going to have to know this unit circle. It's a very handy thing to have in your back pocket. And if that doesn't, encourage you to do it, well, it's going to show up on your final exam. So when in doubt, there's your motivation. So this is equal to sine of pi, but what is sine of pi? Well, that's just 0 minus sine of 0 is just 0 again, minus cosine of pi is negative 1 minus cosine of 0, which is just 1. So that's equal to 0 minus negative 2, which is just equal to 2. See, knowing your antiderivative is only half the battle here. You find the antiderivative, but then you have to know what to do with these limits, and then you have to know your trig values here to combine them, and then you have to simplify it down to get your final answer. So there's a lot of moving parts when you're doing these things. So when you're doing this problem, the best thing to do is not to try and do too much at one time. Take your time, go step by step, be methodical, be meticulous, and you'll get your answer, all right? So make sure you know your derivative rules as well. Knowing the derivative rules will drastically help your integration. If you don't know your derivative rules, how on earth are you going to be able to undo this? So, got to know those integral rules. All right, now let's try this example. The integral from 0 to 1 of x divided by 1 plus x squared dx. All right? So, when we look at this, well, there's a couple things that probably pop into our head. How can we break this fraction up into different pieces? Well, unless you know complex analysis, that route's not going to work. Okay, what about a power rule here? How about we try and do that? Well, no, that's not going to work either. Ooh, what if we integrate the numerator, integrate the denominator, and then take that final answer? That is wrong. So many ways, it's not even funny. It's not even funny. Do not take the integral of the top and divide it by the integral of the bottom. Don't do that. Please don't. Thank you. Please don't do that. All right, so here's what we are going to do. We're going to crank out the magical tool known as U substitution. It's going to be your best friend when you are integrating. So U substitution is what you use when you have no clue what else to do. You don't recognize it as a derivative rule or integration rule. You don't have a power rule for it. You don't have the natural log for it. It's not some kind of trick thing that you recognize. So when in doubt, U sub. But only do that if one of those other rules does not seem to work. All right, so here's what we're going to do. When you have the integral of a rational function or a fraction right here, the denominator is most likely going to be your problem. We can handle numerators pretty well. The denominator is what's going to give us a problem. So that's what we're going to let u equal to. So I'm going to let u equal 1 plus x squared. Then du is just 2x dx. Remember, this is u substitution. Pick a u, find a u, and we're going to change our variables in here. So we can rewrite this integral as the integral from a to b, because we're changing variables, so we have to change our limits of integration, but I'm just going to call them a and b right now, because I know there's there, I just don't know what they are yet. Now, we want to get a du in here, because we have x divided by u dx. We want to integrate with respect to u, but we're integrating with respect to x in this problem. So we need to figure out a way to get this du in there. Well, du is equal to 2x dx, right? And we already have an x and dx in there. So what I want to do is I'm going to stick a 2 right in there. Now I have a 2x dx, and that's my du. But the problem is I can't just go around and plugging 2's in places and just move on with my life. Can't do that. If I'm going to multiply by 2 inside, I have to multiply by 1/2 out in front. Remember, multiplying by 1 and adding by 0 are the two most powerful things you can do in mathematics. So if I want to multiply 2 on the inside, I have to multiply by 1/2 on the outside. And so this integral becomes 1/2 the integral from a to b of du over u. Now, from here, we have a decision to make. Notice how we've left these limits of integration as a and b so far? Well, now it's a problem. Now I can't leave them on any farther. Before, I could kind of coast along with that a and b, and it wasn't a problem. Now it is. So here's the decision. When we change the variables, the limits of integration change. So, should I go ahead and calculate the new limits? Actually figure out what a and b are? And then I can just plug it into whatever my antiderivative is? Or do I just do this entire thing in u, find my antiderivative, and then sub back in for u, and then use my original limits of integration? So here's what we're going to do. For this problem alone, I'm going to show you both ways. So let's do this. So we're going to go down 2 branches right here. So I'm going to do 1 in red. All right, no, what, that supply is bad. I'm going to do 1 in blue, and then we're going to do 1 in green. So this first one, what I'm going to do is I'm going to sub back in for x. So I'm going to keep my a and b here because they're not going to be around forever. Here's what I mean by that. So from here, this is equal to 1/2. Now what's the integral of 1 over u? Well, that's the natural log of the absolute value of u from a to b. All right, cool. Now from here, since everything's in terms of u, I want to go back to x. So I'm going to sub back in for u. I know u is equal to 1 plus x squared, so this becomes 1/2 the natural log of 1 plus x squared, and evaluated at my limits. But since I'm back in terms of x, I'm no longer in terms of u is forgotten. We're back to our original limits, 0 to 1, and then this is equal to 1/2 times the natural log of the absolute value of 2 minus the natural log of the absolute value of 1, which is equal to 1/2 times the natural log of 2, because that guy is just equal to 0. So my answer is 1/2 the natural log of 2. All right? Now let's see it the other way. What happens if, we're with u, I'm committing to u. So that's what we're going to do. I need to change these limits of integration. These limits, 0 to 1, are in terms of x. So now I need my integral in terms of u. So what I'm going to do is change my limits of integration to u of a to u of b of du over u. What's u of a and u of b? Well, that's these limits in terms of x plugged in here. So we have this relationship between u and x. So when x is 0, u is equal to 1. And then when x is 1, u is equal to 2. So from here, this is equal to 1/2 the natural log of the absolute value of u evaluated from, well, u of a. Well, sorry, that's supposed to be u of 0. My apologies. If I confused you there, I deeply apologize. We plug in 0 into here. So that's just 1 plus 0 squared, or just 1. And then we plug in 1 into here, and we get u is equal to 2. So it's equal to 2. And now we do the fundamental step where we take our limits and plug them in. So this is 1/2 times the natural log of the absolute value of 2 minus the natural log of the absolute value of 1, which is equal to 1/2 the natural log of 2, since that is 0. Both equally valid ways. You can do it both ways. Why? Because actually, they're the same thing. They are. You just do it in a different order. Here, we evaluate our antiderivative first, and then sub back in. Then we plug in our limits. But over here, what we do is we change the limits, then we evaluate the definite integral. Notice you plug 1 and 0 into 1 plus x squared both ways. It's just a question of order. So they are 100% equally valid ways. That's personal preference. Do you want to just keep things in terms of u and then sub back in to x and keep the limits of integration the same? So u is a placeholder, map to u, do your work, come back to x, and then do your limits of integration? Or when you substitute in for u, do you want to just commit to u and just stay there the whole time and then change your limits of integration and plug it in? You do the same steps every time. It's just an order preference. So no matter which way you do it, they'll get you to the same answer. All right, now let's try this definite integral. The integral from 0 to pi of secant x times tangent x dx. All right? So there are a couple ways to do this one. You could rewrite this integral as the integral from 0 to pi of 1 over cosine of x times sine of x over cosine of x dx, which is equal to the integral from 0 to pi of sine of x over cosine squared of x dx. Let u equal to cosine of x. Find du is equal to negative sine of x, and la 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 la. And continue about u substitution of the normal process. Or we can recall one simple formula. the derivative with respect to x of secant of x is equal to secant x tan x. Remember when I said knowing your trig rules will drastically help you? You can do it this upper way, but when you have to go through that much effort to do that, why bother? You should already have these derivative rules memorized because, well, you need to know these derivatives. We've been doing these derivatives for a couple months now. So you should already have that formula memorized. And then it's just recalling what is the integral. Well, the indefinite integral is just the antiderivative. The derivative of what got you to where you are? We're here, so the question is the derivative of what, which in this case is secant of x, got us to secant x tan x. So that's what we're going to do. We're going to use that formula instead because that formula is something you should know. This isn't some weird trig formula that I pulled out of a hat. This is something you should know. So we can conclude that the integral from 0 to pi of secant x tan x with respect to x is just equal to secant of x evaluated from 0 to pi. So now we have to evaluate secant at 0 and pi. Well, what is secant? That's just 1 over cosine of x from 0 to pi, right? And now we plug in pi and 0. Well, that's 1 over cosine of pi minus 1 over cosine of 0. Now from here, well, that's just equal to 1 over negative 1 minus 1 over 1, well, that's just negative 1 minus 1, which is equal to negative 2, right? So, simple and straightforward as that, right? Nope. In fact, this integral does not converge. If I can spell converge right. This integral does not converge. Why? Because we made a crucial mistake. We weren't really paying attention to what we were doing. We just started integrating willy-nilly and just went about our day. We just recognized that formula, plugged in the endpoints, and called it a day. But we can't quite do that now, can we? Why is that? Take a second and think about this. What are the requirements of the function that we are integrating to actually integrate? What are our requirements? Think back to the fundamental theorem of calculus. Think back to just the fundamental theorem of calculus. It requires that the function to be continuous on the interval in which we are integrating. We are integrating secant x tangent x from 0 to pi. So another way of thinking about that is we are integrating from 0 to pi of sine of x over cosine squared of x dx. But to do this integral, on this interval, we need sine of x divided by cosine squared of x to exist everywhere. We need to be continuous. But there's a problem. Pi over 2 lives in here. Pi over 2 lives in there. And cosine of pi over 2 is actually equal to 0. So actually in this interval, there is a division by 0 in there. That's not a hole, it's a problem. There's a pole there. There's an asymptote. So this function is not continuous on the interval 0 to pi. At pi over 2, this function breaks. There's a pole there. You can actually graph it. You should look at it sometime. Pull it up on Wolfram Alpha or the Desmus calculator or something like that and graph this. This integral does not converge because the function is not continuous on the interval. The function is not continuous on the interval, so the integral does not converge. Since we run into that pole, it kind of skyrockets off towards plus or minus infinity. We cannot integrate this function on this interval. We can still find an antiderivative, that's no problem. The antiderivative is secant of x. It's evaluating the fundamental theorem of calculus on this interval. See, sometimes when we do this, we get a little lazy. We forget what we're doing. This is a shortcut for calculating the area under the curve. It's our way of calculating it. So you just think about the endpoints. What is secant doing at the endpoints? We forget what happens in the middle. It has to be continuous from 0 to pi, which secant x tangent x is not. So you got to be careful on that. And so this example, it does not converge. All right, now let's try this example. The integral from 0 to 1 of 2x e to the x squared dx. Now, in differentiation, we love e to f of x. E to the derivative of e to the f of x is just e to the f of x times the derivative of f of x. It's a beautiful rule. We love having it. But when you're integrating, it gets kind of messy. It's like he's trying too hard to be helpful. It's an integration that actually gives the hiccup. So whenever you're integrating a function times e to some other function of x, the safest thing to do, let u equal to that function that's in the exponent. So in this case, let u equal x squared. Whenever you're integrating a function times e to some other function, let u be that other function. 9 times out of 10, that'll get the job done. Won't always work, but 9 times out of 10, that's the function you want to set u equal to. And so now we calculate du is equal to 2x dx. And so what do you know? We already have a 2x dx in there. So this integral is the integral from u of 0 to u of 1 of e to the u du. Well, now this is just equal to the integral, or just equal to e to the u from u of 0, which is just 0, to u of 1, which is just 1. All right? Why is the integral of e to the u e to the u? Because the derivative e to the u is e to the u. And now we just evaluate the endpoints, so we get e to the first minus e naught, and that's just equal to e minus 1. When you're doing these integrals with a function times e to some other function, let u equal to that function up here. 9 times out of 10, it'll get the job done. All right, now let's tackle this problem. The integral from e to e squared of 1 divided by x times the natural log of x. Okay, this is kind of a gross one. But remember, with these, don't get bogged down in the woods. Go step by step. Ask yourself, when we're integrating this, what's the problem? What do we not have a rule for? We know how to handle 1 over x. That natural log of x in the denominator, that's what's giving us a problem. And what's giving us a problem, that's what we let u equal to. So let u equal to the natural log of x. Then du is just equal to 1 over x dx. Ooh, this is working out beautifully, because as you can tell, we already have a 1 over x in here. Now, I might be wondering, how on earth did I know to do that? Practice. When you do literally thousands of integrals, you start to get the hang of it and recognizing what you want to let u equal to. That's the trick to integration. Practice. Practice, practice, practice. All right? So this integral becomes the integral from u of e to u of e squared of 1 over u times 1 over x dx. Well, that's just equal to the integral of u of e, but that's just the natural log of e, to the natural log of e squared of 1 over u times du. Excellent. So 1 over x dx, well, that just goes to du. I plugged in e and e squared into my u because I am changing the limits of my integration because I'm changing my variable. Now, this is equal to the integral of 1 over u, but that's just the natural log of the absolute value of u evaluated the endpoints. But what's the natural log of e? Natural log of e is just 1. Just something you got to know. The natural log of e squared, that's just equal to 2. Properties of logarithms. Pull down the 2, and so you get 2 times the natural log of e, which is just 2. If you're looking at this and you have absolutely no clue where I got these limits from, shoot me an email. I'll explain it in more detail. Now we evaluate the endpoints. So this is the natural log of 2 minus the natural log of 1. But what is the natural log of 1? Well, that's just 0. So this whole thing is just the natural log of 2. All right? And once again, if you have any questions on any of these examples, you have no clue what I did, shoot me an email and say, hey, on this review, this number, I have no clue what you did. Can you explain it in more detail? I'd be happy to do so. So, pick u to be the problem, which in this case is natural log of x. Find du, sub it in, change my limits, evaluate my integral with respect to u, plug in my new limits, simplify, and voila, I have my answer. All right, let's try this example. The integral from 0 to pi of sine of x cosine x with respect to x. Now, You might want to pass the integral to each term individually and then take their product. Do not do that. Can't do it with derivatives, can't do it with integrals. When we're multiplying together, we cannot do it that easily. So when you have something like this, pretty much the only thing you can do is use substitution. But what are we going to let u equal to? Are we going to let u equal to sine of x or cosine of x? Here's a little secret. It does not matter. You can actually pick u to be either one of these, and then you'll get your answer. So really what we want to do is pick a u that makes this problem the simplest. I'm going to let u equal to sine of x. Why did I choose u to be sine of x and not cosine? Well, du then is just cosine of x dx. If I chose u to be cosine of x, then du is negative sine of x. Then you have to deal with negatives. You have to multiply by -1 times -1. Just a hassle I don't want to deal with. So I let u equal to sine of x, and du is equal to cosine of x d of x. How did I learn how to do that? Practice. You eventually just start picking up these little tricks like that, what you want to set your u equal to. So now that we have our u, we want to reevaluate this integral. So this integral becomes the integral from u of 0 to u of pi of u times cosine of x dx. Well, that's just equal to the integral from u of 0, which is just sine of 0, to u of pi, which is just sine of pi, right, of u du. Now, to simplify these limits of integration, well, that's equal to the integral from sine of 0, but what's sine of 0? Well, that's just 0. What's sine of pi? That's also 0. So this is the integral from 0 to 0 of u to u. So these limits are the same thing. We're basically asking, what is the area under the curve from 0 to 0? So what is the area under the curve at a point? Well, if you remember your properties of integrals, that is just equal to 0. The integral from 0 to 0 of something is equal to 0. So we don't have to sub back in. So this is why I prefer to do my limits of integration first. Evaluate those. See what they look like. Because sometimes they might actually save you a lot of work. So when I did this integral, so let u be sine of x, du is cosine of x, change my limits of integration, recognize my new limits are from 0 to 0, or the same thing. And when you're integrating at a point, so from a to a, well, that integral is just 0. That just comes from the properties of integrals. All right? Now, you could do the whole process. It'll get you the same answer, but this way is a little bit faster. All right? I think that's enough of definite integration. So what we're going to do now is not definite integration. We are now going to do indefinite integration. Technique's still the same thing, but we just are not evaluating the endpoints. We're not using the fundamental theorem. We're simply just finding antiderivatives. And since the process is the exact same as the definite integral, just less steps, we're only going to do a couple examples of this just to shake the rust off from doing indefinite integration. So let's start this off. First example, let's look at the indefinite integral of secant squared of x dx. Now in this one, there's pretty much only one way you can do this problem. Recall, the derivative with respect to x of tangent of x is equal to secant squared of x. That's pretty much the only way you can do this problem. So you have to remember your differentiation for your trig rules. You have to know them well enough so you can go backwards. Remember, antiderivative, it's asking the derivative of what got me here. Since the derivative of tangent x is just equal to secant squared, then we know that the antiderivative of secant squared of x is just tangent of x. But see, that's not my answer. It's tangent of x plus my integrating constant c. Because when you take the derivative, the constant vanishes. So when you integrate, you don't know if there was a constant originally there. You don't know what that c is. C could be 0, c could be pi, c could be 17 trillion. You do not know. So when you do the indefinite integral, always make sure that you tack on this houseboat, this integrating constant plus c. You just do the integration the exact same way you would, just tack on a plus c at the end, and so that encompasses all of the possible antiderivatives of your function. How to check? Take the derivative of tangent x plus c. You'll end up back at secant squared. Now let's try this example. The integral of the natural log of x divided by x. All right? Well, remember, we're taking the indefinite integral, so we don't have to worry about limits of integration here. So let's look at this. Do we have a rule off the top of our head that we can use for this? No. No, we do not. We do not have a rule for this. Enter u substitution. Now, the trick with u substitution is picking what you want u to be equal to. Well, let's look at here. We have something divided by x. X in the denominator is not really a problem for us. We know how to handle that like it's nobody's business. Integral of 1 over x is not a problem. It's that natural log right there. That natural log is giving us a problem. So we're going to let u equal the natural log of x. Then du is equal to 1 over x dx. Remember, just calculate the derivative of the natural log of x. That's 1 over x. Multiply it by dx. So we get du is equal to 1 over x dx. And what do you know? We already have a 1 over x in there. So our integral of the natural log of x over x dx is equal to the integral of u, let's go ahead and break this fraction up, is equal to u times 1 over x dx, but this is just du. So this integral is the integral of u du. Now we're integrating a variable with respect to itself, and we know that this variable has power 1. So now it's time for the power rule of integration. So that's equal to the u to the 1 plus 1 divided by 1 plus 1 plus c, our integrating constant. That's equal to u squared over 2 plus c. However, when you're doing a problem like this, and you're doing indefinite integration, if you start at an x, write your answer in terms of x. When you are doing a definite integration, you don't need to worry about that because your answer is going to be a number. It's not going to be in terms of a variable anymore. It's just going to be a number. But when you're doing indefinite integration, end up back in the variable that you started with. You start in terms of x, end in terms of x. Start in terms of t, end in terms of t. All right? So here we just recognize the problem in this. The natural log is giving us a headache. Let u be that. Calculate du. Sub it in. Do the power rule of integration. Sub back in for u. And we get our answer is the natural log of x squared divided by 2 plus c. Don't believe that's your correct answer? Take the derivative of your answer and make sure you end up back at the natural log of x divided by x. All right. That's all I got for you guys today on this review for integration. I'd like to point out, you should not just study these examples. These are not comprehensive examples that encompass every single possible question you might come across. There are literally hundreds of kinds of questions that we can ask for these problems. These just go through the basic gist of the kinds of techniques you'll need to work with. How to deal with exponential functions, logarithms, trigonometric functions, polynomials, natural logs, things like this. Got to know how to work with them. So, if you need a lot of practice with these, we have this review, you have the homeworks, you have the lecture examples, you have the entire lecture dedicated to integration practice where I literally just calculated 30 integrals. So there are a lot of examples out there. And if you've come across another worksheet or something with more examples and you want to work them out, if you want me to check your work, I'm happy to do that. If you want to work some examples out, send them to me to grade. I'd be absolutely thrilled to do so. All right? Remember, I am here to help you. So if you have any problems with integration, definite or indefinite, do not hesitate to ask, because this will show up on your final exam. You will have to do integration on your final exam. You also have to integrate in Cal 2 and Cal 3 in differential equations, but that's beside the point. I'm worried about the thing that's coming up next week. All right, guys. That's all I got for you today. So if you have any questions, let me know. And actually, I think this is my last audio lecture. So I guess it's my last lecture for you guys. Well, in that case, just want to say I had a lot of fun teaching you guys for the half of the semester I got to see you. You guys were a fun class. I actually missed getting up there in front of you and lecturing. And I wish the best to you all, and I hope to see you around Tech sometime in the fall or this summer. All right. If you have any questions, please don't hesitate to let me know. And I will see you next time I see you, where we will have more fun with math.